Hi, I'm Jim Heffron, and these are my lessons in Calculus 1. Again, we're going to do homework today. Today is the homework on the continuity section. I happen to be doing only 4 problems, but as always, I want to note that one of the problems is taken from a prior section. So in this case, the prior section is the definition of limits, so a little different than some of the examples that we've done before, where I took some from chapter 1, which was not actually ordinarily included in my course. But so now we're down to having done enough material that we can go back to prior sections that we've done. Okay, and always very important to keep bringing them up so that you have them in your head. The way you remember things is by frequently recalling them. Okay, let's get started. Okay, so a rare moment of sun here in Vermont in November, almost unheard of, but don't worry, it'll go away soon. So let's see, I'll start in. I'm doing section 2.2, number 15, and let's see if I can dig the darn thing up here. This is the book. Again, just to have mentioned that the book here is the Stewart Calculus book, very, very good book. There are a number of very good books, but this is one of them. And here I'm looking at the limit as x goes to 1 from below of f of x equals 3. And then also the limit as x goes to 1 from above of f of x equals 0. And then f of 1 is equal to 2. And the instructions say sketch a graph of a function that satisfies those conditions. All right, let's see how I do. So I'm looking for the limit as x goes to 1 from below of f of x to be 3. So I'm going to draw a graph. The action happens around a equals 1. And I want the limit as x approaches a from below of f of x to be 3. So maybe something like this. Okay. And then the second part says the limit as x goes to 1 from above of f of x is 0. So x goes to 1 from above is 0. So something like that. And then the last thing they want is that f of 1 is 2. So they want me to darken in that one right there. Okay, so just trying to remember what the words limit as it goes to 1 from above, those kind of words mean. All right, that's all. So just have recalled them briefly to our mind. Didn't pick the hardest problem, didn't pick the easiest one. And now moving on to the new material, section 2.5. And the homeworks are number 5, number 11, and number 25. And again, I just kind of picked a selection and deliberately picked odd numbered ones so that a person can look up the answer in the back of the book. Let's see how I do here. I gotta move something out of the way. And number 5, where is it? So number 5 says the graph of the function f is given. Here we go. The graph of the function f is given, and it's given right down here. Okay. It says at what number a does the limit as x approach a of f of x not exist? At what numbers a is f not continuous? And at what numbers a does the limit as x approaches a of f of x exist, but f is not continuous at a? So at what numbers a does the limit as x approaches a of f of x not exist? It seems to me that that when you look at a equals 1, there's a jump discontinuity. So the limit is one thing on the left, it's another thing on the right, and so because the two sides don't agree, because the two sides don't agree with f of 1, you have that it's discontinuous at 1. What about here? Well, that's actually x equals 3. So at x equals 3, there's a limit from the left, there's a limit from the right, but it's the same. However, it's not equal to f of a, but it doesn't matter. It's the same, so the limit is whatever that number is. They don't have the y-axis labeled. So the limit exists. It's part B where it says at what numbers is f not continuous. So f is not continuous at 1, but also f is not, because the limit doesn't exist there. F is not continuous at 3 because although the limit exists, the limit doesn't equal f of 3. Okay, at what numbers a does the limit as f as x approaches a of f of x exist, but f is not continuous, so we just said that. That's the input x equals 3. Okay, great. So that was number 5. Number 11, I gotta move this thing. It weighs about 1,000 pounds. There we go. And it says the toll T charged for driving on a certain stretch of a toll road is $5, except during rush hours between 7 a.m. and 10 a.m. and between 4 p.m. and 7 p.m. when the toll is $7. Sketch a graph as a function of the time measured in hours past midnight. Hours past midnight. Forgive me. And then it says discuss the discontinuities of the function and the significance to somebody who uses the road. So let's see. I'm supposed to sketch a graph of as hours past midnight. So I'm drawing a graph that goes from 0 to 24. Okay, and what are the dollars again? It's $5 and $7. So 5 and 7. All right, and then the function has a value of 5 everywhere except between 7 and 10. 7 and 10. And also everywhere between 4 and 7. Okay, so we're looking at value of 5, and then it jumps up to 7, and then back down to 5, and then jumps up to 7, and then back down. They don't tell you what happens exactly at 4 o'clock. But so these are discontinuities. There's a discontinuity at 7, a discontinuity at 10. There's a discontinuity at 4 and a discontinuity at 7 p.m. All right, and it says discuss. Those always make me nervous. Discuss the discontinuities of this function and their significance to somebody who uses the road. And the answer is that if it's 6:59 in the morning and you're coming up on the toll, you're like, oh, let's go, you got to get there before 7 o'clock. Is that the price changes with no intermediate value? It's not like for a couple minutes it's at some intermediate value. That's not right. Okay, great. So that's number 11. And then the last one for the day is number 25. And again, I got to pull it over. Here we go. Number 25. Show that f has a removable discontinuity at x equals 3, and then redefine f of 3 so that f is continuous at x equals 3, and thus the discontinuity is removed. I don't know why they have removed in quotes as though it were an embarrassing word. Let's see here. So f of x is 25. F of x is it is x minus 3 over x squared minus 9. And I know we've all been trained to factor these things, and so x minus 3, we recognize the difference of two squares is x plus 3 and x minus 3 on the bottom of the fraction, and we see that the fraction the fraction does indeed have trouble. It has trouble at minus 3, but it also has trouble at x equals 3. So at x equals 3, the n minus 3, this function is not defined. Okay, this function is not defined. Fcn is function. But we know that because the x minus 3's cancel, that we can define, we could, if we want, plug the hole at x equals 3. So we could redefine, so I'm going to call it f hat just to give it a different name, that's all. And it's going to be here the original definition of x minus 3 over x squared minus 9 when x is not equal to 3. And then I'm going to define it to be, let's see, what should I define to be at x equals 3 to plug the hole? Well, at x equals 3 here, if you cancel the x minus 3's, then you're looking at 1 over 6. 1 over 6. So that's what I want. I want 1 over 6. And I've plugged the hole in that way. Now, I haven't plugged the hole about x equals minus 3. That's not what the question asked. So I plugged the hole by putting in a 1 over 6. Okay? Okay, very good. So those are the homeworks for continuity. And next we're going to start in on a new section. Very good.